every act of creation is first an act of destruction. It's a quote that perfectly captures the absolute mind-bending turning point we are witnessing right now in modern computing. For decades, we all relied on a pretty simple rule. You shrink the transistor, and your computation gets faster, cheaper, and better. We called it Moore's Law. But to make way for a completely new, unimaginable era of hardware, Moore's Law didn't just quietly fade away. It was actually dismantled by its own success. To really understand what's replacing it, we have to kind of shatter this illusion we have of invisible code. We tend to think of artificial intelligence as just software, right? Like beautiful, abstract mathematics floating effortlessly somewhere up in the cloud. But let's be real for a second. Every modern AI model starts its life as heat. It starts as physical reality. We're talking about melting copper, massive data center power grids, and giant cooling towers. The intelligence is entirely material. And right now, that material is literally running out of room. Okay, let's dive into this explainer and explore the post-Moore era. We're looking at a profound structural shift where AI is no longer just running on chips, it's actively designing them. And even more incredibly, we are actually moving away from electricity itself and beginning to compute using light. Here's our roadmap for today. We'll follow a modern chip's life through 6 stages. AI's physical reality, AI enters the fab, the copper bottleneck, light moves the data, computing with light, and finally, the reciprocal era. Part 1, AI's physical reality and the end of linear progress. For years, we all kind of believed this very linear story. Better chips just mean better AI. And when you send a prompt to a large language model today, somewhere out there, a building the size of a city block pulls just a little more power from the grid. Inside that massive building, thousands of accelerators trade trillions of floating point operations per second to give you an answer. And sometimes, that's all just to help you write a polite email to your boss. This is the true substrate of intelligence. Copper heating up, silicon switching, photons landing, and megawatts upon megawatts of power being dissipated. But this brute force approach has absolutely hit a physical limit. Moving on to part 2, AI enters the fab, reversing the causality. Because we can't just rely on humans manually shrinking transistors anymore, we have to send AI directly into the fabrication plant, the fab, to solve problems that human math simply cannot handle. To wrap our heads around this, let's look at something called inverse lithography technology, or ILT. In modern chipmaking, what you draw on the mask is definitely not what you get on the silicon wafer. Because of the absolutely crazy physics at a 5-nanometer scale, you have to project this heavily pre-distorted hologram through mirrors and optics just to get the basic shape you actually want. So ILT is this brutal inverse problem of working backward from that desired wafer pattern to figure out exactly what bizarre, alien-looking shape you need to print on the mask. And this brilliantly illustrates the paradigm shift we're talking about. In traditional ILT, we modeled that entire optical imaging chain using classical numerical methods. At these extreme microscopic scales, this was computationally brutal. It took impractically long, even when running on supercomputers. But now, AI has literally entered the chat. Chipmakers have replaced these massive, clunky numerical solvers with neural surrogates. These are AI models that learn a highly compressed representation of the imaging physics. This provides an orders of magnitude reduction in runtime. The physical machine hasn't changed at all, but the shapes it prints are now chosen by an AI that learned to see the exact way the machine sees. But this shift goes way beyond just printing shapes. It's completely revolutionizing layout optimization. Following a massive breakthrough published by Google back in 2021, commercial electronic design automation tools absorbed a radical new intuition. Layout optimization is learnable. Today, we're using reinforcement learning for chip floor planning and graph neural networks to ruthlessly reduce wire length. Why does this matter to us? Well, at a scale where a single 1-nanometer edge variation can entirely ruin a chip, the rigid, rule-based systems of the past were just choking on their own complexity. AI is now an absolute requirement to navigate these incredibly brittle layouts. So, we are successfully using AI to print these unimaginable architectures on silicon. But that leads us to a massive midpoint question. Even if this perfect lithography were totally free, what happens when the data gets too heavy for the copper wires connecting these chips? Which brings us to part 3, the copper bottleneck. We've hit a communication wall.
You see, modern AI isn't just limited by the chips themselves, it's heavily bottlenecked by the communication happening between the GPUs, the servers, and the racks. In late 2024, data rates reached an astonishing 244 gigabits per second per lane. But here's the catch. Pushing that much data electronically creates tremendous physical resistance. Because of this, the reach of passive copper cables has shockingly dropped to below a single meter. We're talking about cables that can barely reach across a standard office desk without losing the signal to heat. There is no way we can build massive data centers if the cables can't even reach out of their own server rack.
Which forces the industry's structural answer in part 4, light moves the data. The room full of light. To get past this copper wall, we have to stop just pushing electrons around. We need silicon photonics. Let's define this clearly so we're all on the same page. It is the technology of integrating optical components right onto the silicon chip using standard fabrication. This allows our data to travel as light. Imagine carving microscopic channels called narrow waveguides right into the silicon itself. They act as tiny on-chip optical fibers. By moving data as light, you completely bypass the ohmic losses, the electrical resistance that you naturally get with metal wires. Now, what's really interesting about this slide is how fast this is becoming reality through something called co-packaged optics, or CPO. Instead of sending electrical signals down a long motherboard just to turn them into light later, CPO places the optical transceivers directly on the accelerators themselves. And guys, this isn't science fiction. Deployment-ready products are hitting the market in 2025. NVIDIA's Quantum X platform is utilizing integrated silicon photonics right now to support an absolutely staggering 115 terabits per second of switching capacity. The efficiency gains here are just wild. By moving from conventional pluggable transceivers to these new co-packaged optics, the industry is targeting an astonishing 80% reduction in energy per bit. The data center is no longer just a cold room full of computers. It is actively evolving into a room full of light. But wait until you see the next step. Part 5, computing with light.
The interference pattern.
This is perhaps the most mind-bending concept we're covering today. Light is no longer just shuttling data back and forth, it is actually beginning to do the math. Welcome to the era of photonic AI accelerators. Because so many core AI operations essentially boil down to linear algebra, we can actually multiply and accumulate numbers using the physical interference of light propagating right through a chip. Look at these incredible real-world demonstrations. Light Matter's Envise chip performs matrix multiplication using 512 light beams across 200,000 optical components. MIT successfully demonstrated a photonic processor that executes deep neural network computations in under half a nanosecond. And researchers at the University of Sydney have used a nanophotonic chip to classify complex biomedical images at up to 99% accuracy. So the crucial point is weighing these incredible strengths against our current physical constraints. Photonic accelerators offer massive throughput and incredibly low energy use because the actual physics of the light itself is doing the heavy lifting. However, the major constraint today is precision. An optical multiplier currently achieves the equivalent of maybe 4 to 8 bits of precision, but modern AI models usually train on 16 or 32-bit floating point numbers. Closing that gap requires constant, real-time calibration of every single microscopic component. So for the near future, these chips will act as highly specialized coprocessors. They'll do the heavy linear math, while traditional silicon continues to handle the memory and control. And that brings us to our resolution. Part 6, the reciprocal era. The Ouroboros of modern computing. Just look at how our very definition of computation has evolved to escape the purely electronic domain. Back in the Moore's Law era, the unit of compute was the individual transistor. You shrank it, you won. Simple. Then, as data centers scaled massively, we entered the packaging era, where the unit of compute actually became the optical fabric connecting all the GPUs together. And now, as we push headfirst into the photonic era, the fundamental unit of compute is becoming the interference pattern of light itself. The fab, the package, and the compute are now entirely intertwined. What replaced Moore's Law isn't just a new line on a graph. It's a beautiful, symbiotic system. Think about this loop for a second. The exact same fabrication plants are printing electronic transistors and optical waveguides on the exact same wafers. AI models running constantly in the background are training on the physics of those very fabs to help draw better, impossibly complex chips. And those new chips are then incorporating light to move and increasingly compute the data for the next generation of AI models. It's like a giant puzzle perfectly clicking into place. It is the ultimate feedback loop. The intelligence and the light are now designing each other. And it leaves us with one incredibly exciting, provocative question to walk away with today. If human mathematics took us to the absolute limits of the transistor, what impossible realities are we going to uncover now that machines and light are co-evolving? I hope this explainer shed some light on the subject for you. Keep questioning, keep learning, and I'll see you next time.